Hello, everyone. In this lesson, I'm going to finish off the concepts related to electricity, and then we're going to move into magnetism. So the first thing we're going to talk about is the idea of power in circuits. And we're going to talk about what power is and how it's related to the variables we've already talked about in electrical circuits, the ones you like the ones that you worked with during your lab last week. And then we're going to look at how much power do these things consume, and also how much does it cost if we want to actually power some electronics that we might use. So the concept of power is actually a rate. So it's the time rate of change of energy, or another way of saying it is the rate at which an appliance uses energy. So we have things which use power, such as refrigerator, stove, that sort of thing. But we also have things which supply power. So things like generators, which you might have in your home. Actually, you might have a dedicated generator for emergencies and that sort of thing. It's a good thing to have. But also power plants, which we don't often see because they're usually a little bit far away from where people live. So in that case, in the case of a generator or a power plant, the rate at which energy is supplied is the power. The more energy we use, or the faster we use the energy, the more powerful the appliance is. So power is the rate of using energy, or another way of saying it, power is the rate of doing work, right? That concept of work that came up in our third unit on energy in society. Work is relates to a change in energy. So here is our basic definition of power. Power equals work divided by a change in time. Or you could also say power equals, it should actually be a change in energy divided by a change in time. I'm not sure what happened there. So the second equation should be P equals delta E over delta T. And our units are a little tricky here because we're going to introduce a new unit. I know this energy has units of joules, and time has energy of seconds. So our power is going to have units of joule per seconds. And now we give this unit a new name, and so there's a new derived unit, and that is called the watt. So anytime we talk about power, we're using the unit of the watt. When we talk about electrical power, we could actually get several equivalent expressions. So it's fine and all to talk about energy and time, but when we're talking about our circuits, we don't have energy and time directly. We have things like voltage and current and resistance. So in that event, we actually have an equation that looks like this. Our power is our voltage times our current, or if we use different variations of Ohm's law, right? Ohm's law, voltage equals current times resistance. And then we can get the second version of this. Power equals P equals V squared over R, right? Power equals voltage squared divided by resistance, or power equals current squared times R. So all of these are equivalent expressions. It just kind of depends on what you have to start with that you might use to calculate your power. Doesn't matter which version of this we use, the units are always going to be the watt. So let's look at a problem here. We have a little light bulb, and it's being powered by a 1.5 volt battery, and the light bulb has a resistance of 0.75 ohm. Okay, and it's connected in a series circuit there. That's cool. First thing we're going to do is calculate the power used by the light bulb. Well, fair enough. So here I have I'm given the resistance, 0.75 ohm, and I'm also given the voltage, 1.5 volts. So I want to use some version of the equation that involves those two variables, resistance and voltage. So if I'm not mistaken, there is one like that. So if you can just go back and look at it, you do the quick calculation, and you should get 3 watts. Okay, 3 watts is the answer there. And then for the second part, we can say how much current paces, oh, typo there, how much current passes through how much current passes through the light bulb? Okay, well, again, we don't actually need the power for this one. All we need to know is the original resistance and current. Sorry, resistance, I apologize. The resistance and voltage, and then we're going to use Ohm's law, right? Ohm's law, that resistance equals voltage divided by current. And figure that one out, right? Maybe do a little bit of rearranging, figure that one out, and you should get 2 amps. You may not realize this if you've never had this conversation with your parents, but I don't know, all those electrical appliances that consume electricity, they cost money, right? So you're going to have to pay the power company, which around here is either, depending on where you live, it's either Hydro Ottawa or Ottawa Hydro or Ontario Hydro. So how much does it cost? The first thing you need to realize is that the electricity companies are going to charge you based on the number of kilowatt hours of energy that you use. And it's usually once a month, right? You usually get a bill once a month, and it just basically tells you how many kilowatt hours, which is kind of like a unit that only electrical companies use, generally speaking, but it's a unit of energy. Okay, so kilowatt hours is a unit of energy. So instead of using joules, right, which is what we would use in physics and other sciences, they use this unit of kilowatt hours, but still a unit of energy. And I'll show you how that works in just a second. Okay, so what they do is they basically tell you, this is a very simplified electric bill, but it kind of gets the point. They basically say, okay, well, this month you used 1,300 kilowatt hours, and each kilowatt hour is 14 cents. And so multiply those out, and you get a bill for your month of $182, which would make me lose my mind. That's a lot of money. That's a lot of money for an electric bill. But I mean, I suppose it depends on how much you use electrical appliances. The meaning of the kilowatt hour is basically you use 1 kilowatt of power for 1 hour. Okay, so if you remember that power is energy divided by time, that's the definition. Power equals energy divided by time. If you were to multiply power by time, then you would get back energy. So that's the basic idea here. A kilowatt is a unit of power, and an hour is a unit of time. Okay, so we're not using the normal units that we use, right? We're not using watts, we're not using seconds. We're using kilowatts and hours. So there you go. That's the relationship between a kilowatt hour and a joule. So you can see like that multiplier there. It's enormous, right? We're talking millions of joules. Okay, so let's say that we actually wanted to figure out how much an appliance was going to cost us to run. So here's some more numbers. The electric company charges 14 cents per kilowatt hour, and our coffee maker has a power rating of 1,050 watts. So even though it has all this other information there, like this might be there's usually a sticker on the side of the appliance that tells you, what the voltage requirement and how much current it draws. That's just to make sure that it's not some weird, like, I don't know, European thing that uses a different kind of voltage. So that's neither here nor there. If you bought it in North America, it's going to work in your outlet. That's not the problem. So in terms of this question, all we really care about is the number of watts, which in this case is given as 1,050 watts. Okay, fine. Now here's the equation that we're going to use to figure out the cost. So the equation is energy multiplied by unit cost. Energy multiplied by unit cost. Okay, fine. So what does that mean? So the energy, that's the thing that's going to be in kilowatt hours. So we have to first take our appliance, our power rating of 1,050 watts, and convert that into kilowatts. So the easiest way to do that is to just divide by 1,000, because that's how you go from watts to kilowatts. So we're going to divide that by 1,000. Okay. Then we also need to know how many hours we're going to use this for. Now that's not given yet in the question. I wonder if that's the next thing that's coming up. Okay, here we go. So we're going to use the coffee maker 1 hour per day, like in the morning, I guess, when folks like me need it. 1 hour per day for 30 days. So we're going to assume it's a 30-day month. Okay, so that means that the time that we're going to use the coffee maker, we need that in hours, right? For the kilowatt hour unit, you need to know your time in hours. So 1 hour per day for 30 days, that's going to be 30 hours. So when all is said and done, the energy for this one is going to be 1.050 kilowatts multiplied by 30 hours. Okay, that'll be the number of kilowatt hours. And then if you multiply that by 14 cents per kilowatt hour, you get your answer of $4.41. Okay, if you have your textbook available, or if not, it's on the Google Classroom, then try a couple problems just to make sure that you have this concept down. One thing that's actually really important about these power calculations is that, the cost calculations, like I did a moment ago, even though it's a calculation and we're in science class, so we would normally apply significant digits, for power cost calculations or energy cost calculations, you're always going to round your answer to the nearest cent, right? The nearest 100th of a dollar. And that's simply because when you get the bill, that's what they do, right? They round it to the nearest cent. They're not gonna. So when the power company does it, they don't follow significant digits, right? It's a money calculation always gets rounded to the nearest cent. Okay, so now we're gonna switch and talk about electromagnetism. All right, electromagnetism is basically this intersection of electricity and magnetism. So this first part here is just going to go over some of the basics of magnetism, and then in the next lesson we're going to dive deeper into the concepts of electromagnetism. Excuse me. Okay, so first up, magnetism. We're going to run through this pretty quick because I'm sure that you remember much of this from your previous science classes. The idea is that when we have a magnet, it has two poles. One is called the North Pole, the other is called the South Pole. And what's happening in this graphic here is we've put some iron filings around the magnet. And iron filings are little pieces of iron that are influenced by the magnetic field and actually make these lines that you can see. So the lines are strongest near the poles of the magnet, and they're weakest far away from the poles of the magnet. So you can see all these lines are going in to the North and South Pole. That's because the North and South Pole are where you have the most lines, and that's because that's where the magnetic field is the strongest. Okay, poles always come in pairs. You can't just have a North Pole by itself or a South Pole by itself. You always have to have a pair, a North Pole and a South Pole. And if you actually cut a magnet in half, it's kind of cool. It's like not a magic trick exactly, it's science. But you get two smaller magnets, right? So, if intuitively you might think, oh, if I cut a bar magnet in half, I would have a North Pole and a South Pole. No, you would actually have two completely separate magnets, each with its own North and South Pole. Okay, so Gauss's law of magnetism says that like repels like. So if we have a North Pole facing a North Pole, then those will repel each other. Okay, you will actually have to try and push them together in order to actually have them touch, which they don't want to do. On the other side, or the other circumstance is if you have opposite poles facing each other. So let's say a North Pole and a South Pole, they like going together. Those opposites attract. Okay, so that's Gauss's law of magnetism, and that's how that goes. Okay, so magnetic field lines, those lines that we saw a moment ago with the iron filings, those are a way that we can draw those in a way to represent the magnetic field and how the magnetic field is arranged in the space around a magnet. So if you look carefully at this diagram, you can see that first of all, it looks like these curves, right? And so these represent the magnetic field lines, and they always start from the surface of the magnet. So we don't typically draw them inside of the magnet. And so they start at the surface of the magnet and they end at the surface of the magnet. Okay, so that's the first thing. So always draw them from the surface to the surface. Don't go inside the magnet. That's not what we're doing here. Then they also have arrows on them representing direction. Now the directionality will make sense in a second, but for right now, I want you to realize that the arrows always point from the North Pole towards the South Pole. Okay, the arrows always point from the North Pole towards the South Pole. So it follows the alphabet. That's the way that I remember it. Okay, the letter N comes before the letter S. So when you're drawing your arrows, you start at the N and you end at the S because that follows the alphabet. Okay, if you were to draw different arrangements of field lines with the bar magnets here. So again, if you have a North Pole facing a North Pole, as in the first case, then those two are repelling each other. And so to show that, we actually have these lines coming out of the North Pole, but they don't touch each other. They don't exactly meet up with each other. They just kind of stop because, well, magnetic field lines aren't supposed to cross each other. That's another thing. So magnetic field lines are supposed to cross each other. So the lines coming out of the North Poles kind of go like this. And then in between them, there's again one of these nodal planes, a plane where if you were sitting, if you had something that was magnetic sitting on that nodal plane, it wouldn't experience attraction or repulsion. It would just, or well, I should say the forces on it would be balanced, so it wouldn't move. If we have the two opposite ends facing each other, so a North Pole facing a South Pole, then you actually have a rather strong magnetic field in between those two poles. As the magnetic field lines go from the North Pole of the one magnet towards the South Pole of the other magnet. Only a very few materials can be magnetized, and if you actually go to the periodic table, you can see that cobalt, nickel, and iron. Cobalt, nickel, and iron all sit in the same row of the periodic table, and they're all next to each other, right? They're all adjacent to each other. So something atomically about those elements is special, and we're going to talk a little bit about why that is. Usually we only talk about iron because iron is very strongly magnetic. In fact, it has its own word, ferromagnetic. Ferro meaning iron, right? Fe for iron. So ferromagnetic materials is usually where we go with this. Okay, so if we were to drill down into a magnet and look on an atomic scale of what's going on in there, we would see something that looks like this, right? We would have localized regions where all of the atoms have the same configuration. And so that's what's happening there. And so the arrows just basically kind of represent a pointing to those atoms, right? They're all kind of facing, are all arranged in a certain direction. Now, the arrows also have another meaning, and that is it goes back to the electrons. So it turns out that electrons not only are important for the concept of electricity, right? You know, moving charges and so on and so forth, but electrons are also responsible for magnetic properties, specifically the spin of an electron. So it turns out that electrons actually spin. So if this was like, if my thumb were an electron, it might be spinning like this, like what was that, counterclockwise, okay? Or it could be spinning like this, right, clockwise. So if our electrons are pointing in the same direction, then you basically have this additive effect, where if I have two atoms with their electrons pointing in a certain direction, and then I would have, you know, a more magnetic quality, and the more atoms whose electrons are all pointing up together, it has even more. So ideally, if we want to have a really strong magnet, we actually want to have all of the electrons or all of the atoms have their electrons pointing in exactly the same direction, and that would give us a very strong magnet. So in that case, the domains of the magnet, we would say, are all pointing in the same direction. All right, so if we go down again and look at those domains, then our unmagnetized substance looks like this. So imagine again that all the atoms, or all the groups of atoms, are like little magnets. So within the larger magnet, we have all these little magnets, and an unmagnetized substance will have them all jumbled up. They'll all be random orientation. But if we magnetize the substance, then everything is in lockstep. Okay, everything is pointing in one direction, and for a bar magnet, that's usually along the axis of the bar. So we have a north pole. So all the little magnets have their north poles pointing in one direction, and the south pole is, of course, pointing in the other direction. If you want to demagnetize something, okay, if you want to demagnetize it, when I say breaking, I'm not talking about like, breaking it in half. If you want to demagnetize something, so you have a bar magnet, and please don't do this with the ones in the classroom because that's annoying. But if you take a magnet and you drop it on the floor, then that will actually cause all of the domains to kind of randomize again. You usually have to drop it a couple times, but anyway. You can also heat it up. So if you think about those, again, those domains as being groups of atoms, as soon as you heat it up, the atoms will start moving faster and faster, and they will start, again, getting out of lockstep and start pointing in random directions. If you've ever done any orienteering, or even just played around with your phone, the map tool on your phone, you may realize that there's a compass in it, and a compass is actually a small magnet. So the idea is that the compass needle actually can be used to figure out what the direction of. Normally we say what direction is north, but a more precise meaning of a compass is it actually points in the direction of a magnetic field line. So this is one of the reasons why we might use a compass in class, is we want to actually know which way do the field lines point, because as soon as we know which way the field lines point, then we can work our way backwards to where the North Pole is. So if you look carefully at this diagram, you can see, as usual, that the field lines go from the North Pole to the South Pole, right? They go like this. They go down from the North Pole. They go out from the North Pole and into the South Pole. Okay, fine. However, what if you had a magnet and it wasn't labeled? You didn't know which way was north and south. Well, in that case, you could take your compass, you could put it near to the magnet, and whichever way it points, that would tell you the direction of the field line. And so as long as you remember that the field lines always go from north to south, then that would allow you to work kind of backwards, right? But use deductive reasoning to figure out which was your North Pole. If you were to put a bunch of compasses around a magnet, this even makes it more obvious, right? So if you have just one compass, it's like sometimes can be tricky. But if you have, let's say, 4, as I have here, then you can really use the magnet to figure out which is your north and south pole. And another way of using them is, if you know which one is your North Pole, you can actually use the compasses to sketch the magnetic field lines. Okay, magnets do come in other shapes. Bar magnets are the ones we most often use in class, but you can also get horseshoe magnets, which have a very strong magnetic field between the 2 poles, right? The 2 poles are the ends of the horseshoe magnet. So really a horseshoe magnet is just a bar magnet that's been folded over itself almost. And the other common geometry is a disk magnet. You see these ones. These are often like on the back of, let's say, like things that you would put up on a chalkboard, right? Like little magnets to hold papers in place or something like that. Those are usually disk magnets. Okay, the last thing we're going to talk about today is something called Erstad's or Erstad's, depending on who you believe. I'm going to say Erstad's discovery. And this was one of the first pieces of evidence that showed a connection between magnetism and electricity. Okay, so far we've dealt with these 2 things as completely separate entities, but it was thanks to Erstad and his observations that we actually see that there's a connection between them. So here it is. And this gets us into this concept of electromagnetism. If you have a conductor with a current moving through it, okay? So in other words, if you just have a conductor and there's no current, then who cares? But as soon as you pass a current through a conductor, that current carrying conductor creates a magnetic field around itself. Okay, so this is going to be my conductor. I'm going to be using this for a bunch of different demos. So here's my current carrying conductor. The idea is, when it's carrying a current, when there's a current moving through it, then all of a sudden there's a magnetic field created around it. Okay? So part of our work is to figure out, or is to know, what is the shape of the magnetic field created around the conductor. So just a quick aside. Here's basically what Erstad saw. So he was teaching at this point. I'm trying to remember exactly the circumstances, but anyway, he was he had a circuit, and for whatever reason, he had a compass needle near to the circuit, and he saw that when when the switch on his circuit was open, so that no current was flowing, the compass would point north, as you would expect. However, once the switch was closed, then the needle would deflect. It would deflect. So if this were, so it's, maybe you can't tell from the diagram. If this were the conductor, let's say that if there were no current, the needle would point north, which in this case is up. And then as soon as he turned on the current, it would deflect like this. Okay, so that's so basically he was trying to figure out, well, what's going on there? Why is the needle being deflected? Well, the only thing that would make sense is if this current carrying conductor all of a sudden created a magnetic field. More investigation with things like more compasses starts to paint a clearer picture. So if you put a bunch of compasses around the conductor, then you start seeing that the field lines actually go like this. They curl around, okay? They curl around the conductor. So in other words, we're going to talk about why this is in a second, but if my thumb is representing the current, right, the current going through the conductor, then the magnetic field lines are curling around like so, okay? So this direction actually turns out to be pretty important. And it even has its own thing. It has the right-hand rule for a conductor. So again, if this is our conductor, I'm going to do this a couple of orientations so hopefully you can see it. My thumb is always in the direction of the current, okay? So in this case, the conventional current, by the way, not electron flow. So conventional current is going this way, then my fingers on my right hand, again, I'm always using my right hand, is going to curl under like this. So this is the direction of the magnetic field, curling around the conductor, right? Curling around the conductor. So it's basically making circles around the conductor. Because it's pretty hard to draw in a reasonable way in 3D, what we normally do is we use symbols to show which way the current is flowing. So if my conductor was like this, right, pointing straight at you, and I wanted to say that the current is coming toward me, how would I represent that? Well, that's A in the slide. The current is flowing toward me or flowing away from you, so we draw that as an X. In the other direction, if the current is flowing away from me but toward you, then we draw that as a dot. Okay, so that's the notation there for current. Again, we're gonna be looking at a lot of conductors and the current flowing through them, and usually we draw them in the cross section. So imagine if I have my conductor and I cut it, I want to know, is the current flowing toward you or is the current flowing toward me? And we're going to use these symbols. In A, you can see that we have the conductor drawn, and the current is I don't really know how to describe that direction, but anyway, the current is, we don't know which way the current is going, but the magnetic field is curling around in the way shown. So what you need to do is you need to try to orient your fingers in the way that it's shown. Now, to me, if I do this, it looks like this. So if I'm looking at it, the current will be going off to the right. The current will be going in the direction of the right. Now, for you, let's see. If you're looking at me, because I think I'm mirrored here in the camera, then you'll be seeing your fingers should be coiling around the back and down the front, right? Around the back and down the front. So in the way you're looking at it, your thumb should be pointing in this direction. Okay? That's my left, but you're right. For B, my fingers are going to be curling up, and that means that my current will be going off in that direction to my right. And for C, I want to figure out, is the current coming out of the page or into the page? So again, if I have my conductor like this, then, oh, that's really painful. Then it will be going into, the page. Yes, the current will be going into the page for C. Oh, right. Okay, so now that we have that down, hopefully, we're going to draw the magnetic field lines around each of these. So for A, again, we have our conductor. Here's our conductor for A. And our finger indicates, our thumb rather, indicates that our current goes into the page. So into the page, so then I'm going to be coiling around in a clockwise direction. Okay? That was actually the last one we did on the previous page. And for B, oh boy, now we're getting really complicated here. For B, my current is going like this. And so my fingers are going to coil so that they go in front and down of the conductor. For C, same idea. My thumb is going to go in the direction of the current, and my fingers are going to coil around like that. Okay. So up, at least the way I'm looking at it, up in front. Up in front. All right, so here's some more questions that you can try for homework. Some of this stuff is going to be on your exit card. So by all means, try these out. And then remember to check out the second video lesson for this week, where we actually dive into some of the more applications of electromagnetism. See you then.